Hi guys, so today I want to talk about the difference between elements and compounds and mixtures and how they're related and how they're different. Okay, now to give you some background here, let's go into the history again. So we kind of stopped talking last about Antoine Lavoisier, and he discovered some elements and law of conservation of mass, that sort of thing. Well, as he's discovering like some elements and making all these discoveries of new substances, other scientists at the time wanted to do the same thing. So they started performing experiments. First one I want to talk about is Joseph Proust. He was a French chemist. He performed some experiments where his goal was to break substances into whatever like they broke apart into, which we now call elements, and measure how much of each element it kind of broke into. Now he noticed that whenever a substance broke apart, it always broke into the same proportions of elements. So, for example, if he took like 10 grams of a substance, magnesium chloride, he would always get the same proportions of magnesium and chlorine that he would if he broke apart 20 grams or 30 grams or 50 grams. He would always get like the same proportions, the same percentages of the elements in each one. This became known as Proust's law. Okay, today we call it the law of definite proportions. A substance always breaks apart into the same ratio, the same proportions of elements, regardless of its source, where it came from on the Earth. Right? Now, another chemist at the same time as Proust, named John Dalton, he was an English school teacher in England. He was doing similar experiments. Okay, he was breaking them apart, seeing what he got. But he discovered that not only do they break apart into the same proportions, if he had a substance and another substance that broke apart into the same elements, which do exist, okay, they would break apart into the exact same elements, but the two substances would give different proportions of each other. Okay, so one substance, say, would give tin and oxygen, and another substance would also give tin and oxygen, and both of them would give the same proportions for that same substance each time, like Proust's law there, but they would also have different proportions from each other. Now, when he compared these proportions, this is a little complicated, he noticed that the proportions were related to each other between the two substances. Okay, they were ratios of each other. So let me explain. Let's say solution or substance number one, you break it apart, you get 20 grams of tin and 2.7 grams of oxygen. Substance two, you break it apart, you also get tin and oxygen. But this time you get 20 grams of tin and 5.4 grams of oxygen. Now, why is this significant? So you got the same amount of tin both times, but the oxygen, you got exactly double of that oxygen. Okay, you had exactly double of that oxygen. So the proportions of these two substances are related to each other. Like the ratio of the tin and the oxygen in each one is a ratio of each other. So the ratio is a ratio. Anyways, this is known as the law of multiple proportions. Okay, and here's a little clip kind of showing a little more examples of this.
Proving that you don't have to be rich to get a law at least temporarily named after you, French pharmacist Joseph Proust built on Lavoisier's ideas of extremely careful measurement, showing that a chemical compound always contains the same proportions of elements. For a while we called this Proust's law, but to make it easier to remember for the world, we just call it the law of definite proportions now. And then an English school teacher, John Dalton, followed Proust by examining what at first appeared to be a problem with Proust's work. Carbon and oxygen, when reacted together, would form two different proportions, not just one. Of course, what was happening is obvious to us. Carbon and oxygen were reacting to form two different compounds, carbon dioxide and carbon monoxide. As Dalton's work continued, he found something truly mind-bendingly fascinating. If you limited the amount of carbon reacting to exactly 1 gram, the mass of oxygen consumed to produce one compound was 1.33 grams, while the mass consumed to produce the other compound was 2.66, exactly double what was required for the other compound. This shook out for other reactions too. When reacting nitrogen and oxygen and limiting to exactly 1 gram of nitrogen, 3 compounds formed. One compound consumed 1.750 grams of oxygen, another consumed 0.8750 grams, and another consumed 0.4374 grams. All of those numbers are relatable by small whole number ratios. Oxygen wasn't reacting with some ephemeral cloud of the idea of nitrogen. It was reacting with individual discrete bits of nitrogen that couldn't be divided. It could react in a number of ways, but it was always the same oxygen and the same nitrogen with the same properties. And so while in our first episode we showed you how Einstein actually proved that atoms exist with super fancy math, Dalton had used multiplication to become the first person to actually have real data supporting the idea of atoms.
So this led scientists to propose what we now call the atomic theory. The scientific theory, it's got lots of evidence behind it, not just what I explained here, but it kind of all led to the atomic theory, the idea that everything's made of atoms. So it's got a couple of parts to it. First off, all matter is made of particles. We call them atoms. Okay? All the atoms of a given element are identical. They're going to have identical properties. Okay? Atoms, these atoms cannot be created, they cannot be destroyed, they cannot be divided. All right? So everything's made of these. All the atoms of one thing are identical. These atoms can't be destroyed. And last, and this gets into kind of the evidence of Proust and Dalton here, these atoms combine, and they combine in simple whole number ratios. So one atom and another atom combine, or one atom and two atoms combine, and they form compounds. Okay? Now, these compounds can be rearranged. So instead of two of these and one of these, we can have like three of these and five of these. They can be rearranged in these chemical reactions, and they'll make a new substance, a new compound, out of those same elements, okay? Or they'll combine with different elements and make different compounds completely. So basically, substances in the universe are all made out of these atoms that are arranged in certain ways, certain numbers of atoms, to make a certain substance. So the way we kind of visualize this, we have atoms, and they combine to make compounds. So basically, matter is made of these single atoms, and in a certain ratio, like one atom of this and two atoms of that will combine to make a compound, which is 2 to 1 for that ratio. You can also have the same atoms which combine in different ratios. For example, you can have a compound between, say, one atom of orange and one atom of green, whatever those elements are. You can also have another compound which has one atom of orange and two atoms of green. That gets into like the law of multiple proportions there. And the evidence shows this. The evidence shows that they're combining in these whole discrete units like this. Right? This leads us into some definitions. So first definition, element versus compound. An element is any substance that is made of only one type of atom. It can't be broken down any further. This is kind of what we were discussing. Take things and break them down. Can't break them down anymore. That it has just one type of atom in it, so one substance there. Compound, on the other hand, this is a substance that's made out of two or more. Okay, so 2, 3, 4 types of different atoms are going to be bonded together. They're going to make a new substance. Okay, so a couple of examples of these. Examples of an element, helium, right? Iron. I have an iron screw right here. So all of the atoms in here are all the same type. They're all iron atoms. Okay. Oxygen. It's in the air around me. It's O2. Now, quick point of clarification. Oxygen comes as an O2 molecule. There's only one type of atom there, but they bond together to form a double molecule. And so those molecules are floating around, but there's still just one type of atom there. So an element is just, there's one type of atom. We've broken it down as much as we can. There's only one type there. It doesn't have to be single atoms to be an element. It just has to all be the same type. Okay? A compound, on the other hand, is going to have two types of atoms, say hydrogen and oxygen for water. Salt, okay? We could have sodium and chlorine. All right? So here's an example of water. Now, water is made out of hydrogen and oxygen. Hydrogen is an element. Oxygen is an element. Those are two different types, and they have different properties than water. Hydrogen is flammable. Oxygen is a gas. Hydrogen's a gas. Okay? Water, on the other hand, completely different substance than hydrogen or oxygen. All right? It's a new substance made with new properties, different from what it was made of. Salt, sodium chloride, made out of sodium and chlorine. So here's an example of salt. It's white. It is a powder. It dissolves in water. All right? And it's healthy. We can actually eat this. However, the element sodium is extremely poisonous and extremely explosive. The element chlorine is a gas. It's actually green. And it's not also very, very poisonous. Not exactly explosive, but they did use it as a biological weapon in World War I and II. So, completely different substance when they combine, though, and form NaCl. It's a compound, a new substance made out of those original two elements. Another one, carbon dioxide, made out of carbon and oxygen. Okay, so kind of drawing these compounds here, just some examples. We got helium there, it's a single atom. We could have iron atoms, a whole bunch of them. Oxygen, 2 atoms bonded together, but still only one type. Okay. And then water, we got 2 different types. That makes it a compound. Right? So this is our first distinction, element versus compound. Now I want to talk about mixtures and compounds. All right, so same information is there for compound. All right, but now I want to talk about mixture. A mixture is 2 or more different substances that are mixed together. Now there's still 2 different substances, so they still have their own unique properties that they did before. Okay, a compound, on the other hand, is one substance, and it's made out of 2 or more types of atoms. All right, so same examples, water, hydrogen and oxygen bonded together, making water, new substance. Salt, sodium chloride, 2 different types of atoms bonded together. Carbon dioxide, 2 different types of atoms bonded together. Mixtures, on the other hand, where you can have a mixture of hydrogen and oxygen, where you take hydrogen gas and oxygen gas and put them together, and they will both be hydrogen gas and oxygen gas, and they will be those 2 things. Hydrogen will still be flammable. They will still be gases. They will not be a liquid, right? So you will have the 2 gases mixed together, hydrogen and oxygen, and they will not be water, because they're still hydrogen and oxygen. Salt, sodium and chlorine, right? Bonded together as a compound, you have salt. Separate, though, you have explosive sodium, explosive or poisonous chlorine, okay? Now you can even have a mixture of 2 compounds. You can take water and you can take salt, and you can mix them together, and you're going to get salty water. You still have salt and water, though, okay? Just because you mix them does not mean that they are no longer the same substances. So a mixture, 2 different substances, still the same substances, though, mixed together, compound, they bond and make a completely new substance. All right, and this is what it would look like at a molecular level. So this, we have a mixture of 2 elements. This is actually oxygen and hydrogen. Okay, they're not bonded, they're separate still, they're just mixed up together. But if they react and they turn into water, now you have a compound of hydrogen and oxygen, okay, where the oxygen and the hydrogen are bonded together in a ratio of 2 to 1, making this little H2O molecule. And that's different from oxygen and hydrogen.
In this experiment, we will first make a mixture of black iron filings and yellow sulfur powder. Black iron filings and yellow sulfur powder are thoroughly mixed. They form a gray mixture of the 2 elements. This mixture can be separated by physical methods. For example, when a magnet is brought to the mixture, it removes essentially all the iron filings, leaving the sulfur behind, which here looks gray because of the impurities from the iron. The iron has been separated from the sulfur by means of a magnet. When the same mixture is heated in a test tube, the 2 elements iron and sulfur react together to form a new compound, iron sulfide. At first, when the mixture is heated, the sulfur melts. Eventually, as the heating continues, the iron and sulfur begin to react together. When the Bunsen is removed, the tube continues to glow as the reaction proceeds. The gray-black brittle solid formed is a new compound, iron sulfide. It is unlike either sulfur or iron and cannot be separated by a magnet.
Okay, so now I want to talk about something called a pure substance. Okay, so a pure substance, what we're talking about is we have only one type of substance there. Right? Now this can be an element or a compound. We already explained those. An element, we have one kind of atom, so people are like, yeah, that's a pure substance, I get it. Compounds, though, are a little trickier. People don't always think this is pure, but it is. So a compound has multiple atoms bonded together, okay? But to It's one substance. It's a new substance. And so when we have a pure compound, we have this compound, and all of the things in there are that compound. So, for example, this would be water, pure water. This is an H2O. This is an H2O. This is an H2O. Even though they're made out of two elements, making it a compound, it's pure because everything in here is this compound. Okay, there's nothing else in here besides this compound. Right? It's pure. This would also be a pure compound. This would be actually sodium chloride, NaCl. And this is sort of a repeating pattern of an NaCl, an NaCl, an NaCl, an NaCl. Now they're all bonded together in one big lump, which is why we just go with the NaCl, because they're equal amounts of both. But it is pure, and there's only one thing there. Okay? So that is a pure compound, just the one thing, an NaCl. As opposed to a mixture, which we already talked about. Okay? Mixtures, you've got two or more substances there. Now, mixtures can actually be broken apart further into something called heterogeneous and homogeneous. Okay? So heterogeneous means it's not going to be the same consistency throughout. Okay, so if I were to grab a chunk of it, I might not get the same ratios of the components. So for example, oil mixed with water, or pizza, or Italian salad dressing. Like if I take a slice of pizza, all right, and it's got pepperoni on it, that's a mixture. It's got several substances there that are different substances, but each slice of pizza isn't going to have the same number of pepperonis on it. I might get one slice with only one pepperoni. I might get one with like 5, which would be awesome because I love pepperoni. But a heterogeneous mixture, it's several substances, or at least 2, but they're not mixed perfectly, so they're not the same consistency throughout. Okay? A homogeneous mixture, on the other hand, it's a mixture, but they are the same consistency throughout. Like it's pretty evenly mixed. This would be something like salt and water. You mix it in there and it dissolves. You still have the salt, you still have the water, but they are, like the salt is perfectly spread out on a molecular level throughout all of the water. They're mixed up perfectly. So each molecule of water and ions of salt kind of mixing together, they're perfectly mixed and they're perfectly evenly spread throughout there. Another example would be pop. Okay, the sugar and the water and the flavoring and the carbon dioxide, they're all mixed together, making pop, which we kind of think of as one substance, but it's a mixture of several substances there. They're just mixed so well that you actually get the same consistency throughout it. Okay, Gatorade's another one. Brass is another one. Right, that's actually a mixture of copper and zinc, mixed so well all the way throughout that it kind of looks like one thing. All the atoms are mixed kind of perfectly evenly, even though they're not bonded. You still have copper and zinc, so it's a mixture. Okay, so kind of a breakdown here. You have matter. Matter can be broken into either a mixture or pure substance. All right. Now, if it's a pure substance, it could be an element or a compound. A mixture, it could be a homogeneous mixture or a heterogeneous mixture. Okay, so kind of separating down here. So I want you to try it now. Pause the video. First, decide, is it a pure substance or a mixture? And then if it's pure, decide if this is an element or a compound. And if it's a mixture, decide if it's heterogeneous or homogeneous. Pause the video and give these 6 ones a try. Okay, so cobalt. Cobalt, it's on the periodic table first off. So that would be pure, just cobalt, and it is an element. Okay, it's not a compound. So pure element. Orange juice, pulp-free orange juice, trying to be specific here. That is a mixture of a bunch of things like sugar and flavoring and water, but it is homogeneous. Okay, as long as it's pulp-free, there's not any chunks floating around. It is homogeneous. They're well mixed. Right? Salad, that's a mixture. It's heterogeneous because it's got big chunks that you can kind of pull out there. Aluminum bromide, that is a compound, so it would be pure. And it'd be a pure compound between aluminum and bromine. They're bonded together to make aluminum bromide. Ammonia. You might not know much about ammonia, but it is not an element. All right. It's pure, so we have a pure substance, just one substance there. It's compound. It's not an element. So pure compound for ammonia. Seawater. This would be a mixture. Okay. It would be a homogeneous mixture. It's one of the examples I had, salt water there. The salt and the water are mixed together perfectly evenly spread.